Well, in the last lecture, we have talked about all the important properties for the matrix operations, like addition, subtraction, multiplication. So in today's lecture, we're going to get on to the most attracting and mysterious operation, division on a matrix. Okay, let's start. All right, so we have understand the definition about the inverse matrix. However, in the actual calculation for the inverse matrix, we will have to introduce another concept called the adjoint matrix, as what is shown here. Okay, so before we can get into the adjoint matrix, we have to introduce another concept for us to understand the adjoint matrix. So it is called the algebraic complement. That sounds something very interesting. What is this? Well, I would say it's actually the derivative of a matrix. So for example, we have matrix A. Okay, so it is just a very common matrix. A11, A12, all the way to A1n. And then we have this one as A21, A22, all the way to A2n. And then we have AN1, AN2, and ANN. All right. For this one, if we do some operation to it, we want to kick this one out. Okay, so we'll draw a line like this. And within this part, we have this. Okay, it seems like we have a new matrix, which is like a remaining, of the line and rows where A11 is kicked out. Okay, so we call it algebraic complement of A. So we will just record it like this. It means this element, is kicked out from its row and also from its column. And what is remaining will become this. All right, so we can do the similar things to in any other elements for the matrix A. So we're going to have many algebraic complement formed. So since we have understand what the algebraic complement is, now we can use this A11, A21, A22, blah 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 blah, many to compose another super, matrix, which looks like this. I would say the A's adjoint matrix. So we understand that A11 means the element A11, small A11 is kicked out from its row and column. And we understand that A12 here, A12 means small A12 has been kicked out from its column and also from its row. So here, instead, because we understand A12 is actually here, so naturally you're thinking we're going to put a A12 here. No, for the capital A12, we're going to put it here in a column like this. And similarly, we're going to put A1n like this. So for A21, A22, and A2n, also in a column format, and all the way to AN1, AN2, and all the way to ANN. Yes, now we have successfully established our algebraic complement. And here, the A1J, we have talked about it. It is the algebraic complement. It is the algebraic complement. Yes, it's algebraic complement. Okay, so here we have to remember one important thing. Well, actually, you don't have to remember it. It is very natural to understand. For any, nth order matrix A, it must has, its adjoint matrix. This is for sure. Yeah, this is for sure. Okay. Okay, in the following, we're going to talk about one important property about the adjoint matrix, which is about A times its adjoint matrix, like this. So to simplify our calculation, we're going to only look at the second order condition. So here we have an second order matrix as A11, A12, A21, and A22, okay? So this time, we have our adjoint matrix, but remember, we have to, actually, transpose it. So A11, so A12. Yes, remember the A12 should be in the same column of A11 instead of, within the same row. Okay, so A21 and A22. Alrighty, so we have established this multiplication formula. Let's try the multiplication. Well, don't be scared. While just following, the regular multiplication rule of the matrix. So this row will time this column. Let's try it. So A11 times big A11 plus the small A12 times the big A12. Well, there's something magic happening. Now we understand that A11 is the element, and big A11 means the algebraic complement, which is a matrix, but is now containing the element A11. The same thing to this A12 and the big A12. And from our determinant calculation methods, if you don't know this previously, please understand that this is nothing but equals to the determinant of A. Yeah, the corresponding element and the corresponding, the algebraic complement matrix, when they multiply together, now we can say that, well, this actually equals to the determinant of the matrix. Okay, so let's try this one too. This one and this one. So this one will become A12 times big A21, small A21 times big A21, and plus A small A22 times big A22. Yeah, the same thing happens. Corresponding element times its own algebraic complement. So we can say this equals to the determinant of A2. Okay, so from the other multiplication, for example, like this row times this column, and we can just take the conclusion that, well, if it is not the multiplication happening between the corresponding element and its own algebraic complement, well, this will become 0. So finally, we can just simply write the answer as determinant of A, 0 here, 0 here, and determinant of A. That's it. Alrighty, so for this guy, it seems like we can extract, well, the common factor out. So we can extract, the common factor determinant of A out as this. Okay? Well, don't tell me that you don't understand it. If you have trouble with it, please review the multiplication operation properties for the determinant. Okay? So this one looks very familiar. Yes, it is nothing but the E matrix. Okay, so before we go, well, let's rewrite this adjoint matrix property again. So here we have the original matrix A, times its adjoint matrix, which looks like this, and like the inverse matrix, which has the commutable property. Yes, here we can also exchange the position of the adjoint matrix and the original matrix. So we'll always have this determinant of the matrix A times the E matrix. Alright, so I don't want to repeat it too many times, but this one is very important. Maybe 1 star is not enough. I would say star and star. Please, this one is very, very important. Alrighty, so after we understand the definition of a concept, now we have to discuss its corresponding properties. So now let's look at the commonly used properties for the adjoint matrix. Okay, so let's talk about the properties. The first one is, what is the determinant of the A's adjoint matrix? Wow. So if you don't understand it, please refer to the definition of the adjoint matrix. Because, just now we said this one is very important, right? So why don't we start from that? Well, let's see. Well, this is actually can be used as the definition, very simplified, precise version of definition about the matrix A's adjoint matrix. So we understand that, for the determinant of A times A adjoint, right? It equals to the determinant of A's determinant times the E matrix. Yeah, this is what we have here, from this definition to here. And from the multiplication properties, we talked about the determinant. We have, this guy, the left side, equals to this. Or to say the product's determinant equals to the determinant's products. Okay? So on this side, remember, we have to be very careful on this. A's determinant is a number, okay? Or just a constant here. So it has to be, multiplied to the E matrix to each column. So from the properties we discussed in the previous lecture, we understand that we have to extract, the determinant of A out, but to the power of n. Yes. Okay. And we understand that the determinant of the E matrix is nothing but equals to 1. Okay, so we have something looks like this. Okay, so that is the first property of, the adjoint matrix. So we can include, okay, so the adjoint matrix A's determinant will become something like this. Okay. And we understand that, well, for this guy, it has the power of 1. So from your basic algebra knowledge, we can simplify it as A's, determinant to the power of n minus 1. Okay, so just remember this one as A's adjoint matrix determinant equals to the A's determinant to the power of n minus 1. Alrighty, so let's look at the second property. Okay, ready? Let's get on to the next property. So this one is kind of similar to we have discussed before. I've just put a constant k here, and k is a non-zero number. So I would say k times a. So can you find out the adjoint matrix for me? Well, anyway, so we have discussed this before. So every time you are confused, refer to the definition. So here, let's look at this. So Ka, we will take that as a whole matrix, okay? So it's adjoint matrix. Okay, so on the left side, we have, the Ka, for example. Okay, so this is actually, the definition of the adjoint matrix. Okay, so we have this one, Ka times E, okay? All right, so let's simplify this. Remember, the properties of the determinant of matrix. So we have K here. So if we want to extract K out, remember, we have to, put the nth order here. And then we can say this, and E, okay? All right, so on the left side, we have a K to the power of 1. On the right side, we have K to the order of n. So now we can have, this one and this one canceled out like this. And also, we can put a inverse here to cancel out this a. So we have to put a inverse on the right side too. See? So now we have the Ka matrix adjoint as a inverse times k to the order of n minus 1, and then a e. All right? So let's do something magic. Because, this e times this matrix will not change anything. So we will just cancel this e out, okay? So what about this one? Can we do something? Okay, so from the definition of the adjoint matrix, we can deduct that the A adjoint matrix equals to determinant of A, E, okay, and on the left side we have 2 times A inverse, because on this one we can do the A inverse here to cancel out this A and this A, okay? Okay, so that's why we have the A star, or to say the A adjoint equals to A inverse times the determinant of A and the E, because the E times this will give us the A inverse again, so we can just write it like that. Okay, so for the same reason, okay, so this guy can be further write as A inverse A, because they're all the determinant A is a number, so we can do the commute operation. So, and this one will give us A star times K to the power of n minus 1. Okay, so that's it. We can put our conclusion here. So the K times A's matrix adjoint will become, okay, so K, which is a number, we put it on the left, to the power of n minus 1 times matrix A's adjoint. Okay? All right, so for the next few properties, I will just write down the conclusion without giving the proof. You will say, would it be very hard to remember? No. It's actually very easy. It's hard to prove, but very easy for us to remember. So for example, if we have the A transpose star adjoint equals to A star transpose. So it seems like we can just commute the operations here, right? So the operation of the star and transpose are commutable. So what about this one? Inverse operation. So A transpose inverse equals to, yes, A inverse transpose. Yes. And then also, for this one, we have A inverse adjoint equals to A adjoint inverse. Alrighty, so we can say that this is very easy for us to remember, and we're gonna do a very simplified conclusion for the major operations on the matrix, which is about the inverse. Okay, I'll use another color. Inverse, okay, transpose, and adjoint. These operations are all commutable. Yeah, so you can just remember this. So every time you see the star, t, and -1, we'll call it inverse. You can always put them back and forth. It doesn't matter. Okay, so let's look at the property number 5. So this one is actually the interesting one. So we have a star and then another star. So for the property 1, we talked about the stars, the adjoint determinant. But what about this? Okay, so it seems like we have referred to our definition again. Okay, so from this one we can see that A's adjoint equals to A's inverse times A's determinant. So we can take the A star as a whole as the A in that definition. So in this case, we can have it as A stars determinant times A stars inverse. Okay, so for the A star, it can be further expanded as for this one. From the property 1, we can understand that it equals to the A's determinant to the power of n minus 1. Okay, and for the A star, we can further expand it as, from the definition, A's determinant times A's inverse. Okay, times A's inverse, and then times, okay, it's to the inverse. Alrighty, so now we can further expand it as A's determinant to the n minus 1 power, and we can put it like this one, like this, because this is just a number, and this one will become A. Okay, so this one and this one has the same base, so we can just combine that power as A n minus 2 and then A. Alrighty, so you can see that to the if we put one star here, we're gonna do a lower order here. Alright. Okay, so the problem number 6 will be more interesting. Okay, let's look at this. Remember, we talked about the rule called the put on and take off rule. So let's look at the general version of this. So if we have A times B, so we want to look at its adjoint. Okay, so this time we can simply write it as B adjoint times A adjoint. Yeah, so we put on B late, but we have to take out B first. Okay, so A, B, okay, transpose. So we can simply say B transpose times A transpose. And also we have the same thing for the inverse. So we have B inverse times A inverse. So you can see that, well, for the major operations, star, transpose, and inverse, they all obey the, the put on and take off rule. Okay, so that's it. Alrighty, so we've been talking about theory for about 1 hour, so it's time for us to jump into the example. So now we have a matrix, which is a 3 by 3 matrix here, and look at this magic condition, given as A, I, J, which is the element in this matrix A. It equals to, the A, capital A, I, J. Wow. We understand that capital A, I, J is the algebraic complement, right? So each element just equals to its algebraic complement. So what does that mean? Okay, we'll talk about it soon. And also we have, A33 as -1. Wow, this is much simpler. At least we have a specific number. It does not sound that sounds, too abstract for us. Okay, so now we want to find out A's determinant. Wow, seems like we have to, integrated all the definitions and properties we have learned so far. Okay, so let's take advantage of this condition. What does this mean? All right, so from the adjoint matrix, we understand that we have a connection between the element in a matrix A and its algebraic complement. However, in that case, remember, we say that, for matrix A, we have this A11, A12, and A1n. And we have A21, A22, and A2n. This one we have AN1, AN2, and ANN. Okay? For the adjoint matrix, now we have it as A star as A11, but we have to put it as in a column like A1, 2, yes, and then we have A, all the way to A1n, and then we have A21, A22, all the way to AN2. 2n, sorry, 2n. And here we have AN1, AN2, all the way to ANN. Okay? Yeah. So it seems like, we have to do some transpose here. So if, each element, equals to its corresponding algebraic complement, it just means we just have to, do the A transpose, like to turn this to the left or to the right 90 degrees. Now we have the A transpose equals to A star. Okay? If you have a little trouble with this, you can compare like this one equals to this one. Here's another color. And this one equals to this one. This one equals to this one. So what we have to do is to do the transpose to make the A star equals to A transpose. Okay, starting from here, let's put into the definition of the adjoint matrix. Okay, so from the last session, we have something like this, remember? So A times its adjoint will give us the A's determinant times the E matrix. And here we have the A transpose equals to A star. Can we take advantage of that? Yes, of course. We can simply, adjust, replace A star here with the A transpose. Well, let's look at it. Equals to A times A transpose equals to A's determinant times matrix E. Okay, since we want to find out the value of determinant A, so let's transform all the matrix A into its determinant. Well, confused? Well, that's actually very easy. Well, let's just put the determinant sign or the operation on each side of our equation. Okay? And also from our multiplication property of matrix determinant, we have this one as products determinant equals to the determinant's products. Okay? So for this one, because determinant A is a constant, or to say a number, so we can extract it. So out of the determinant operation, so we can have something like this. Okay, and we understand that the matrix E's determinant will be 1. So this one can be further written down as A determinant. Okay, but here remember, if we times this constant number to the matrix, right? And also we understand our matrix is a 3 by 3 matrix. We always have to put the order here, 3 and 3 here. Alrighty, so as we understand that the determinant of a matrix is like its inner characteristic. So for example, so we understand that the geometry definition of the determinant, for example, here, right? We have two vectors, so it's nothing but the area, right? So even if you transpose, like you write something like this, the area within these two vectors will not change. So that's why the determinant of A and the determinant of A transpose will be exactly the same. So let's deduct, well, this one as A square equals to determinant A's cube. Okay, so let's put everything onto the left side of the equation. So I would say this one minus the determinant's cube equals to 0. And we can further extract a common factor determinant A out as 1 minus determinant A equals to 0. Okay, so this time to make this function successful, so we can conclude that determinant A, because it's just a number, so it's like a very regular equation for us to be 0, or determinant A equals 1. Yeah. So which one will be the final answer? Yes, we will have to refer to the other condition here. Yeah, the A33 equals to minus 1. Okay, so how can we take advantage of that condition, which is about A33 element equals to minus 1? Well, remember, previously in today's lecture, we have talked about the algebraic complement and how it can help us to find out the determinant of a matrix. Yes, so we can also find out the matrix of A by using this element A33. So now let's see. So if we take the A33 as the center, so let's expand it in a row where the A33 is. So A's determinant will become A31 times its corresponding capital A31, and plus A32 times the capital A32 and A33 times the capital A33. And then let's double check, because each non-element Aij equals to capital Aij. See? So actually we can simplify this as A31 square, A32 square, and A33 square. right? And also, we already know that a33 equals 2 minus 1. So this can be simply converted to this. Okay, so for each square, from our basic algebra knowledge, each square will be either equal or bigger than 0. So for this whole thing, the determinant A will be either equal to 1 or bigger than 1. Okay, so which answer will be our final answer? Yes, this one. And this one will be deleted. Alrighty, so that's the whole step to find out, determinant of A for this question. You got it? If you have a little trouble, pause the video or, rewind it and repeat it till you really understand, including the properties we talked about in today's lecture and in previous lectures. It's not that hard, believe me. If you really understand the properties we have talked about so far, you can do it too. Okay? Keep the momentum up and enjoy the linear algebra. See you next time.